Okay, hello everybody. So today we have, as you know, we are going to change the focus a little bit more, and we are going to mainly talk about the project. This week would be the project week, um, and the plan is to first start giving you a high-level project description. So you already know much more detail because we shared with you the paper beforehand. Um, but Ying and I wrote a project description as we shared today on GitHub. And we plan to, first of all, walk you through the high-level presentation about the overview of the work. And please make sure that you ask your questions because it is important to fully understand the approach and the details that you require. Um, and also, the plan is to also on Thursday, Ying is going to walk you through some code, some details of the framework from the implementation perspective, so you get a better understanding how to start, how to approach this project. So before we start, do you have any question? I hope my sound is clear.
Yeah, your sounds good.
Okay. Uh, is there any question here, or I can
I
skip?
did have one. I didn't see any deadlines for the tasks yet. I didn't know if those just hadn't been made yet.
Yeah, that's a very good question. So Ying is going to share with you the deadlines either today, probably she's going to share today or on Thursday. Um, so yeah.
Yeah, I will share the deadlines for each task today.
Okay, thanks.
Yeah, after the presentation, I think.
Yeah, thanks, Ying. Is there any other questions? Okay, let's start. Today, it's my pleasure to talk about our work on Athena, which is ensemble defense, consists of many diverse weak defenses. And here, diversity and also the several weak defenses are two most important aspects of this framework, which this defense is built upon. And this work is a collaboration between several fantastic people. This work, as you know, is led by my student, Ying, who is also a TA for this course. Jianhai is also helping a lot with this project. We started actually this project in collaboration with Jason, and recently Forrest and Biplov also joined this endeavor. And I also play a very, very small part of this. And to be clear, I gave this talk initially to Google so weeks ago, so I'm going to use the same slides. So I will skip this. We don't need to talk about those. But basically, this work is about the security of ML, and more concretely, the security of deep learning. But in general, this framework and the topic of adversarial machine learning is not only about deep learning systems, but in general for any machine learning system. And the reason that it got the attention, as you know, many deep learning systems are being deployed and is already deployed on real world scenarios. And that's why showing that they could be attacked and they could be defended. So this makes it a lot more concrete and more interesting. And that's why the scenarios that we are going to discuss is about deep learning. So we talked about adversary example. I'm not going to spend much time on this, so we can skip probably most of this, but to give you again some idea, we discussed that typically when we talk about adversarial example, we have a particular input. This input could be an image in this case, but it is not specific to image at all. And then we generate some perturbation based on two aspects. First, the input itself. So you see the input appears as a part of the generation process, but also we need the correct label of the input, as well as some information that we can get from the model. This is mainly the gradient of the loss function. So basically, intuitively, this optimization use in what direction if somebody added some small perturbation, you can change the decision that has been made by the model in order to trick it. Intuitively, we talk about classifiers, so already you have some intuition what is a classifier, what is a decision boundary, but schematically, you remember we had, for example, in the case of binary classifier, we have some examples, right? Based on these example, you build a decision boundary. What's going here is that you have one of these examples. In order to trick it, you want to add some perturbation in order to basically change the decision boundary in order to classify this as a negative example. So the trick is to fool the model by moving the example throughout the decision boundary in order to trick the model. And it's the same. People have shown that even you can trick the model even by flipping to certain degrees. Also, people have tried to use 3D printer in order to show that it is not necessary to be digital image, but could be physical things as well. So you could print out this turtle to be classified as a rifle. Yeah. We have several other fantastic work showing that you can also 3D print out these eyeglasses in order to identify, in order to fully classify, as well as trying with different voice recognition systems. The same for RL and NLP tasks. So it's the same sort of idea. And this could be really, we discussed about this as well, this could be really important because if we deploy such systems in practice for self-driving cars, this could be really dangerous if somebody could fool these models in order to trick a self-driving car. So that should be really bad. We now discuss some intuition where these adversarial examples come from. So basically, this is these are sort of foundation that you already have about classifiers, machine learning models. So typically, we start by some data. We represent it by D, and then some of these might be related to different classes, right? In this case, we have 3 classes of examples, some oranges, some palm trees, and some chimpanzees. And then we have a model, in this case, a neural network that we talk about, and you know that these neural networks are parameterized by some weight values. So these are the weights or parameters of the model. And then we could try, right? We could select, after we train the model, we could select some example, some input example with its true label. We tried one version of the model, and that's why we have theta 1. It means that we use one specific version of the model to see what we get, right? So this version of the model classify this as boundary, which is obviously incorrect. Maybe we want to retrain the model or add more example, and maybe now try with different model and see whether the prediction has been corrected or not. And in this case, yes, it classified this example as orange. So this means that this model is good enough. And the overall approach, again, we discussed about all of this. Now, a little bit more abstract is to find some optimal parameters that the expected loss. So this loss is the expected error that the model makes with respect to the example that come from a specific distribution, right? So this is the distribution T, and we need to plug in these optimal parameters in order to calculate the loss. So basically, this is a search problem. So we are seeing here that we need to find the optimal parameters in order to minimize this expected loss over all examples that coming from this distribution. And more specifically, even though the aim of the training is to find these parameters that minimize this loss, we already know how to do it, right? We discussed extensively about gradient descent. That is an algorithm, iterative algorithm that find these parameters for us. But on the other hand, you could think about this as a game where the adversarial goal is on the total different direction. The adversary tries to, and this is a specific adversary, right? To be clear, in this case, the adversary can change the input. We assume, like by this formulation, we are talking about very specific assumptions in this problem. We are assuming that the adversary, for example, cannot change the parameters directly, right? Otherwise, we would say it here. We assume that the adversary can change the input data to a certain extent, right? And that is defined by this LP norm of this perturbation. So the adversary tries to find some small perturbation where, on the other hand, maximizes the loss in this case, right? That's the key objective of the adversary. So it's working on the other direction, which is, you can think about it as a game kind of situation, which both have different objectives. Do you have any question about this? So I presume this should be really familiar with you already. And that's why we specifically try to build this foundation for you, that you be able to do the project at this point, that you already have these foundations. So I'm going to talk specifically about Athena, which is this framework you're talking about. And this is really based on the intuition of input transformation, meaning that we want to make some changes to the input example somehow. And to give you the idea of why it works and the idea of using input transformation as a defense mechanism has been out there before this work. And the key idea is that let's imagine the adversary found some small perturbation that could change this input. You see that some noise has been added, okay? Comparing to this. That could trick this classifier, this model that classify this example as 9 with certain confidence. And this is the probability that the classifier puts for digit 9. So you see that previously model thought that the input is 7 by relatively high confidence. Now the model thinks that it is 9, but somehow moderate confidence. And the role of this transformation is to change the, to add some noises in the input. We discussed like these perturbations are not random. On the other hand, this comes from a specific formulation as optimization, maximizing the loss, right? So this is not just random perturbation. Random perturbation doesn't work. These are some very carefully crafted perturbations. And this rotation in this case basically misplaced these noises. So we expect that these noises, these perturbations are not as effective as before. And that's why in most cases, like these transformations, in this case, this is a geometric transformation, more specifically rotations, can change the decision has been made by the classifier that now thinks that it is 7 with some relative moderate confidence. Okay, so that's the key idea behind why transformation works in the first place. And to be clear, like people have shown it previously. But what is the key insight of this work? The key insight is on the complementary aspects of many transformations, or many weak defenses as we call them. So here, what you see is that you see different adversarial attacks with different names, right? So these are the names of different adversaries. And here on each row, you see different transformations, right? So you see compression, denoising, filter, geometric transformation, morphology, and so on. So let's see what we got. So this is some empirical understanding of what's going on here. So if you notice some transformations here, like compress, is able to recover the label quite correctly, right? So you see that like these attacks were able to trick this model in all situations, right? So in this FGSM changes that it thinks it is 9, 9, 9, 8, 9, 2, 9, 9, 9, right? So in all cases, the model, the undefended model, has been tricked. But here you see that like compression, we're able to recover the true label in all cases except this one, except 1 pixel example that has been generated by 1 pixel. But some other transformation like geometric transformation in this case were not as effective. So it was able to recover few, but again, it was not effective for some other attacks. And if you look at here, we have some different, transformations. The interesting part here is that, for example, in this case, noise were able to recover relatively okay, especially if it's able to recover this 1 pixel that was not able to be recovered by this compression. So you see that some transformation complement each other already. Based on this, so we see that the effectiveness of weak defenses varies across different attacks. And also they have this tendency to complement each other, and like you can look at it from the column wise. So based on this intuition, we thought at the beginning of the project, when we were like 2 years ago, almost 2 years ago, we thought, okay, maybe if we put together some of these transformations to create an ensemble of weak defenses. Weak defenses in this case is the same as transformation, but we build a model based on the transformation. I'm going to describe how. Then this could be potentially a strong defense because we did not assume any particular information from the attacker. So we did not build this defense based on some pre-assumption about the attacker. And that is important when we want to deploy such defense in the wild, because in cybersecurity work, if we consider some assumption, this typically would not generalize, and someday a new attack comes that totally behave differently from previous attacks, and that could change the whole thing. So this is about the inside, but more specifically, we looked at the quantity and quality of the weak defenses. In this plot, you see that we increased the number of weak defenses. So on particular axis, you see that, for example, in this, each point here shows the test accuracy of the defended model, right? In this case, this blue line shows the case where we select these weak defenses in a worst possible case, right? What would happen if we select them in a very bad way, meaning that we have some alternative, we select the worst one, right? This is the best scenario where we select them very carefully. And this is the random case where basically we select these from the pool randomly to see what we get. So we observed that really, so in this case, quantity, as you increase the number of weak defenses, no matter what, we increase the test accuracy, even in the worst case. But also quality matters, right? So you see like quite a wide gap between the worst case and best case, right? So both quality and quantity of the weak defenses matters, and most importantly, diversity was something which is super important. So in this case, we compare the error rate of the defenses that comes from that the attack comes from 1 pixel, a particular type of attack, and we compare this with two different defense. One is basically the baseline defense. This is PGDA. It is one of the best defense out there in the literature. It's based on adversarial training, which people have shown that is really effective. And the adversarial training is the case where you generate some adversarial example with a specific type of attack, and then you mix it with the training example, and once you have the model is really effective. So you cannot really fool the model unless you have a very clever attack mechanism. So this has already been shown to be a state-of-the-art attack. And then we tried and also compared with some version of Athena, but in this case, instead of putting together a diverse set of weak defenses, we select different variation of shift, meaning that we put together ensemble, but instead of having a diversity, we put together a homogeneous ensemble model to compare how important diversity is for building such effective defense for us. And we saw that diversity matters. In this case, you see the error rate of the diverse ensemble is quite much better than homogeneous, as well as the state-of-the-art baseline defense. So as you increase the number of weak defenses, this gap also tends to increase as well. Is that clear? Do you have any question about this? Because this is important. So already I show you the quantity, quality, as well as diversity is important for building such kind of adversarial defense. Do you have any question about this?
Sorry, can you hear me?
Yes.
In the last slide, the key, it mentioned high K, low K, and then a random average K. Sorry, it's like the slide before. Yeah, this one right here. It shows top K, bottom K, random K, average. What does K exactly mean again?
So here means that we have a certain number of weak defenses, right? So imagine that we have 70 weak defenses, right? And here we need to select 10, right?
Okay.
So you can select differently, right? So you want to select 10 out of 70, right? So you have quite a number of selection alternatives. So basically we tested out all possible scenarios. The worst case, this is reported as the worst case. Best case, this is as the base case, and random is when we randomly select from this. Does it make sense?
Yeah, that clarifies it. Thank you.
Sure. Very good question. Any other question here? Very well. Make sure you ask your question, right? This is the time because these questions matters for your project. But also, we observed the same on, like, this one was about 1 pixel, but we also tested out with different type of attacks, DIM, MIM, PGD, and most importantly, if you look at PGD was the attack that has been used for adversarial training, PGD ADT, and you saw that even in this case, Athena was able to get better result, reducing the error rate, even with the scenario of PGD attack, and that was quite important result. So let's discuss a little bit about the architecture, and specifically what do we mean by weak defense. Weak defense is simply a name for the model that we trained on the transformed input. The way how it works is that we have some test examples. We use the transformation, for example, flipping, right? So we flip all of the example in our test set, in our training set, and then we feed it to classifier. This could be a neural network, but not necessarily. It could be a classifier. It could be a neural network, could be a naive Bayes, could be a linear classifier, whatever. And you already know about this, right? And then you build a classifier that is able to classify a flipped images. You do the same for like geometric transformation. You do the same for whatever transformation that you have. So you build different classifier on the transformed images. And the key reason is that one may ask why I don't use the original model. Well, you could use, but typically when you flip or do some changes to the input example, if you try to classify the example by the original model, maybe even these transformation may fool the model, which this is not what we want to do, right? We do not fool ourselves. we want to have some mechanism that able to block adversarial examples. So that was about the design time. Now this is the way how the difference works at deployment time. Make sure to fully understand this because this is really, really important, right? So at deployment, we use several of these weak defenses, and this is what we call ensemble. So we put together several of these weak defenses, and once an input come to the to this defense, what happens is that it gets transformed differently by different weak defenses internally. And then each of these transformation generates some labels, right? So this transformation thinks that this is 7, 7. This transformation, as we expect, maybe some of them not produce the correct input, correct label, right? And that is expected actually. And then we have an ensemble strategy to decide about the final label. And ensemble strategies, for example, you can consider majority voting, right? So what is the majority of the labels? In this case, 7. You could come up with some other adversarial, some other ensemble strategy. If you know about ensemble machine learning, you can consider many different type of ensemble strategy. And in our framework, we already have implemented some of those, right? For example, averaging across the probability distribution that we get from each of these models. So if these are neural network, each will produce a probability distribution after the softmax, right? So each of these give you some probability distribution, and you get this label by maximizing, by argmaxing, right? By argmaxing this probability distribution of X, right? This is the way how we did it, right? Then instead of using the label, you may want to average all of these probabilities and produce a final probability distribution, right? And then decide the label based on this final probability distribution. That might be very different from the majority voting. Or maybe you want to produce the activation just before you feed it to the softmax and take the average over that. Well, that's yet another ensemble strategy. Or some other, like you could even use the internal layers instead of the last layer. Maybe you want to pick internal layers to decide. Maybe you want to pick random layers, right? Each of these could be a potential ensemble strategy. Even you may want to learn the ensemble strategy based on some past behavior. All of these is possible, right? And we, in this project, we're really looking forward that you come up with some interesting even extension of these ensemble strategies. If you can come up with, you can get A. Right. So some data evaluation results. It got dark here. Okay. Some evaluation results about Athena, and it is important to understand this in cybersecurity research or any evaluation. You need to basically consider a specific scenario, and that's really important. This scenario called threat model. Okay, what we mean by threat model is really is the case where we need to decide what adversary knows about the model, what adversary knows about the internal of the model as well as the defense, and pretty much anything, and what are the flexibilities in this setting, right? To be clear, that we evaluated under 4 different assumption or threats model, and in the project we also need to do the same. Zero knowledge is the case where the adversary, this is the role of adversary, doesn't know that any defense is in place, doesn't know about weak defenses and ensemble strategy, but definitely knows about the parameters of the model, right? This is one thing that the adversary definitely knows about it. And by this we mean that the adversary knows these parameters, so it can calculate the loss over these parameters with any specific example if she wants. In black box attack, the adversary knows that there exists a defense in place, but doesn't know the internal of the classifier, as well as anything about the internal of the defense, but knows that there is a defense in place. And in gray box, the attacker knows pretty much everything, just doesn't know about the ensemble strategy. White box knows about everything. So that's the kind of assumption we are talking about. Some results. This is for. Yes, go ahead.
On the previous slide, my group was talking about this. We were trying to figure out exactly with the zero knowledge understanding of what the target class, like what does knowledge of the target classifier mean? Because in the case of Athena, we train usually, like you said, like an ensemble. We have an ensemble of many classifiers, each of them that have been trained with some different transformation. So we were wondering, what does it really look like? I believe the paper mentioned it was the undefended model, but I really wasn't certain what it meant.
Exactly. So the adversary knows the exact parameters of knows about anything about the model, right? So knows the weights of the model, knows the architecture of the model. So imagine that it has the model, right? It can, but it cannot change the model, right? It knows everything about the model, right? So we can try to give input and get the output. That's the thing she can do with the model. Does it make sense?
Perhaps. So like a model for, this could be a model for image recognition, right? And
right.
Before, you could imagine we could create some model and do this image recognition with no particular thought of adversarial attacks. We could just create a fairly normal, I guess, model.
Mm-hmm.
And it is, and then we could consider another scenario where we create this ensemble of weak defenses, the way it's described with Athena, is the first scenario I described, where we have the parameters that we, and the architecture, the knowledge that would have been done without the context of an adversarial model. Is that what like the attacker would believe the situation is? Is that what we have?
Right. Exactly the way how you describe it, right? So in this scenario, right, let me clarify it better maybe. In this scenario, it knows that, it knows everything about this model, right? So it can gives input and gets output, right? But obviously, this model is consumed by a system, right? That we put some stuff before this, right? So we basically shield the model by our defense. But the adversary doesn't know that there is a defense in place, right? So maybe it generates some adversary example based on the model itself, but obviously there is no guarantee that this adversary example can fool the system, right? Because it uses the knowledge of the model itself, but we shield the model by something else. So we somehow change the model to certain specific, to some extent, right, by the way how our defense works. Right? Does it make sense?
Perhaps a bit more.
Yeah, but it will be more clear once you look at the code, and Ying will explain more detail about the code and everything. But when you look at the code, it gets clear, right?
Sure.
So here what you see is that we use FGSM as one of those that we use a specific type of neural architecture, ResNet, and the data is for C400. In this case, the adversary knows everything about this model, ResNet model. And here you see some result in terms of error rate. Let's clarify what do they show. Here you see some different instantiation of Athena with different ensemble strategy, where we use majority voting, these top two majority voting, average of output, and random defense. And Ying will explain, but for example, top two majority voting is that when we select the top two labels and decide based on that. Average of output when we average over the either probability distribution or the
logics.
Or the logics. It was the logics, right?
Yes.
Right, it was the logics. But technically, you could take average over any activation, right?
Yeah, any outputs from any activation layer. Yes.
Right, and you know that, like, when we talk about neural nets, each of these layers, you have some ZI associated to layer K. So you could use any of these vectors if you want, right? But when you get closer to the end of neural network, probably these are more information is in there. They are more meaningful, you could say. And for these results, we use the logics. Logics is basically the layer activation just before the softmax, just before we pass it through the softmax. And the baseline, you already know, PGD, ADT, the adversary training. Random smoothing is one certified defense, which is also a strong defense. Certified defense is those kind of defenses where you have certification, means that you have some guarantees about this defense. Basically, no matter what, the adversary cannot, make this defense, the error rate goes to above a certain threshold, right? So you have some certification about it. And you see in the result that, right, no matter what kind of perturbation the adversary does, the effectiveness of this certified defense would remain the same. So the result, and also this blue line, this blue line shows the performance of undefended model. So for example, in this case, you see that with this perturbation, this is the parameter of the attacker, meaning that how powerful, for example, is the attacker. You see that the error rate of the undefended model is quite high, is around 80%. The error rate of these defenses is also not that impressive, but this is the error rate of our defense. You see that most of these ensemble strategy did quite well, even comparing with these, state-of-the-art defense mechanism. And this is thanks to the power of, diversity as well as quality of this transformation, as we discussed. But we really observe also similar thing for different type of attacks, different type of zero knowledge attacks. Similar result. I don't want to go into the detail, but yeah. Let's move on to the black box scenario threat model. And again, to clarify, the black box only knows about the existence of the model, but doesn't know anything about the target model.
I have one question.
Go ahead.
Could you describe how you differentiate between a weak defense and a strong defense? Is that a formal definition or kind of an informal definition based on how effective they generally are?
Very good question. So somehow you could think about informal, but basically when we talk about one specific attack, right, when we talk about this attack, it has a parameter, right? These attackers are parameterized. When we increase the epsilon, meaning that how much perturbation the attacker can do, or in other hand, how much changes they can do inside the image. Obviously, the more changes, the stronger they could get, and the stronger meaning that they could increase the error rate. That's somehow the way how you could define it. But if you're talking about different attacks across, for example, if you're talking about these cases, like which one of these is stronger, is really, there are different types. There is no, it really depends. Some of them are showing, some of them are able to fool some sort of model quite well in certain scenario, but some others maybe even works better with different data set. So it really depends on some parameters, right? The data set, the model architecture, the assumption that we have, the specific parameter of each attack. I hope this answers your question. Does it?
Yes, I think so. Thank you.
Thanks. So about the black box, we tried with two different black boxes, and the first one is transferability-based approach. In this case, again, this guy, the adversary, doesn't know the model, but obviously it can approximate the model. It can create a substitute model that emulates the actual model. How? It's easy, right? You can start training a new model. You can give some inputs to the model that you don't know, get some output, use this input-output to train a new model with new architecture, new internal, whatever you want. And then this new model could be a substitute model. And then you could use this substitute model to launch adversarial example with the same approach that you knew before, like FGSM, and then use this adversarial example. Hopefully they transfer to the actual model, and by transfer meaning that they could fool the target model too, right? Is that clear?
Yes.
So this is, I mean, identifying this is quite important because that might be confusing at the beginning, but it's a really simple approach. So basically, use some example to build a model to emulate this target model. And for really creating adversarial example, you need some model because you need to calculate the loss function. And hopefully with this adversary example that you create for this model, they transfer back to here as well. That's the way how it works. Here are some results. On the y-axis, you see some transferability rate. And on the x-axis, you see different budgets. Budgets indicate that how many examples the adversary used to create a new model, right? 1K meaning that it used 1,000 example to feed to the actual model, get the output, and use the same example to build the emulated model. Interesting result is that comparing with Athena, comparing with undefended model, when we used Athena, we were able to decrease the transferability rate comparing with not using Athena, meaning that the defense decreased the transferability rate, which is good. This is what we want to get, right? We want to decrease the transferability of the example that the adversary can generate based on the emulated model back to the target model. This is what we wanted to achieve, and this is what we got from Athena. And each of these shows different, different scenario with different epsilon in this case. This is for BIM attack, but really we saw the same with different adversarial attacks too. Besides this transferability based scenario, we also tested with some optimization based black box attack, in particular hop skip jump, which is a very new attack that appeared this year in 2020. We tested with ResNet again with C400 and different budget level. This is the distance between the adversarial examples and the actual example, right? So you see that when we deployed Athena to defend the model, this hop skip jump needed to perturb the example a lot higher in order to fool the model. And that's bad. Why? Because look at the example. The adversary was able to fool the model with this example, but with Athena in place, it was able to fool the model with this example. And look at this. Anybody can see that this is a perturbed image, right? This is not real. And here are more examples. So basically, it means that in order to fool the model, adversary needs to perturb more, which is bad because any detector, any detection mechanism can identify this that is coming from an adversary. This is not something that the adversary wants, right? Any question about this? Let's move on to the whiteboard scenario. This is basically the case that the adversary knows pretty much everything about the model and the defense in place. Obviously, in this case, no defense has a chance because the adversary knows pretty much anything. So we expected to see some high error rate even for defended model, and this is what we got, right? So this is the performance of Athena, meaning that the error rate as the max normalized dissimilarity would increase. This is the difference between the perturbed images and normal images average across all examples. And you see that as this increases, the error rate of the defended model also gets increased. So the error rate is quite high, which is what we expected to see. But it comes from some, so when we look at the example, I mentioned like this is not easy. So for example, one test that we did was that we used the detection. So you see that here, like we have no chance, right? As we increase the strength of the adversary, the accuracy would decrease a lot. But we trained a detection mechanism, and we were able to identify or flag these examples as adversarial example before even feeding to the system. So, and you see that this is obvious from the example, right? So this becomes obvious that these are coming from an adversarial attack. So with the mix of both detection and the defense mechanism, we were able to build a relatively good defense mechanism that maintain the accuracy across different strengths of the adversary. Besides that, it comes with some cost. The time that it takes for generating one adversarial example, it increases as the strength goes increases. So that's one thing. But also, so this means that this is for one example. So if it wants to generate a lot of examples, it takes really long time. And when we talk about real-time scenario, so it takes a long time. So the adversary don't have enough time to fool the system on real time. So that's one scenario why the time is important, because the adversary doesn't have like much time to generate these examples, right? And within short time, it is impossible to generate with these certain scenario as we discussed. Also, this Athena, again, this is back to the case that we did not assume anything about attacker, generalizes well, meaning that we can change, we discussed about this the ResNet architecture, but we could change the type of architecture, the type of classifier to SVM or random forest, And we were able to get similar results to some extent with some nuances, right? In this case, for example, we changed the architecture to resonant shake regularizer with FGSM and C400 as a data set. And these, again, different ensemble strategies. And by the way, each of these represent the performance of one of those weak defenses, right? So you see that the result is more or less similar, different to a certain extent. Also the same for different type of attack. We also tried with SVM models. With SVM, somehow in some cases, the difference between undefended model and the defended model was marginalized. So basically, some scenario, it doesn't show the benefit as before, but it's still a little bit better than the undefended model. So this shows us that this is quite generalized across different type of classifiers, not very specific to deep neural network, but could be extended to other type of classification mechanism. Also, the other aspect is that obviously it comes with a cost, both in terms of memory and inference time. In terms of memory, since we need to deploy multiple weak defenses, imagine that each weak defense means we have a model with some parameters. We need to store these parameters somewhere, right? And if we have 100 of these models, we need to, and each model, let's say, if they take 100 megabyte, you need to increase that by 100 times, right? So obviously they take n times more memory than before in order to use this defense. But the good news is that it doesn't increase the latency or the inference time because they can work independently. So there is no dependencies between these weak defenses, which is good. So this means that you can feed the example at the same time, you can process and get the result. Obviously, some of these results come at different time. So this is like each weak difference comes at different times. Some of them are quicker, some of them a little bit slower. But all of these, at this case, for the case of MNIST, C400, sorry, the transformation process took less than inference time of the original model. So you can expect to receive this label quite before any one shot of prediction. So this means that we don't increase the inference time because they work in parallel, right? But obviously, you need to increase the memory size for this case. So to summarize, we show that Athena is somehow a good defense mechanism. It is flexible, extensible, right? You can change the weak defenses, can change the architecture. It's general defense, so meaning that it works with different type of classifier. But obviously, it comes with some memory overhead as well. And you know about this, right? The code is there. So Ying, are you ready to share some slide about the project description? So basically, yes. Ying will present you some talk about some of these project description, but she will continue on Thursday about more detail, walking you through the code and everything. But thanks. I will stop sharing now.
Okay, let me share my screen. Okay, so today I will quickly go through this project descriptions with you.
Yeah, can you please
yeah.
make it full screen?
Oh, yeah, sure. Like this?
Yeah, very good.
Okay. Okay, I will go through this project with you. So maybe will help you to understand what you need to do in this project. So basically, in this project, we'll separate the students into 10 groups. Each group may consist of 3 to 4 students, and so each group will build their will build an adversarial machine learning system on top of Athena. So by calling the APIs we provided or extending this Athena, you will need to complete some task to, for example, generate adversarial examples or build some ensemble-based adversarial defenses. So this Athena, I just refactored it last week on top of IBM Arts, so make it much easier to use. I provided wrappers for Keras based classifiers and PyTorch based classifiers. So if you are comfortable to use Keras, you can train your model in Keras, and then we can load your classifier and wrap it into the classifier we recognized. So currently we only support Keras and okay. And in this new structure, I make the ensemble. The ensemble will be treated as a single classifier. So the usage of ensemble will be very similar to a single classifier. And we have implemented 11 adversarial attacks. Okay. So I will push the source code to our project GitHub. So you will get the source code. You can fork from the GitHub repo, and we will provide a vanilla version of Athena. This version of Athena consists of 72 CNN weak defenses, and I forgot one undefended model, also in CNN architecture. Yeah, here. So for almost all the tasks, you only need this the vanilla version of Athena, and that's it. And I will provide baseline adversarial examples we generated for you to evaluate or compare with your approach or results to see whether your output is makes sense or something like that. And I will provide some tutorials, some simple tutorials, tell you how to use the APIs to load single model to load an ensemble to apply this transformations or do the prediction or use it to generate adversarial examples. So basically, currently you only need to write a proper configuration file. We will provide a tutorial as well. So we also provide SVM weak defenses. So this weak defenses are only for this hybrid Athena task. I remember I have trained random forest as well, but last night I cannot find those. Models. So if I find that before the task 2 begin, I will also provide those random forest models. So you will have more options. Yeah, so we will.
But to clarify, to clarify, if you are willing to train model as weak defenses, even with new transformation, you're free to do that, right?
Yeah. Yes.
You can use the architecture. You have access to the training data. You can train a new model, a new weak defense, even based on totally new transformation. And we would encourage that. And then tell us.
Yes, and currently, so in previous version, the transformation, I mean, the parameters are hard-coded, and I have refactored that, so all the parameters are tunable, and all you have to do just to write a configuration file. So you can generate, for example, for the rotation. Previously, we only support rotate 90 degree, 180 degree, 270 degrees. Currently, theoretically, you can rotate by any degrees, by any angles. So just config that angle in the config file. Yes, so for the teams, each team will allow 3 or 4 students, and we expect all the students will participate in this project. So we think don't be so everyone should contribute to your task. We only require 1 submission per team. And yeah, since we have multiple options for task 2, so you for task 2 for I think it's October 15th. Yeah. So the submissions, basically you need to submit all the materials that can, so I can replicate your results without doing any extra work. So basically, maybe the code, the experimental results, for example, the trained, the generated adversarial examples, the trained models, the defenses you built. So anything you think is required to run your experiment. And
to be clear, we tried to specify how you need to deliver. Everything should be through GitHub. So, I mean, if you send us email that, like, here the code, you get no point. Sorry. Like, basically follow the instruction. And if any part is not clear, create an issue. We will address it, right?
yes, yeah. So So basically the code and the project report will be submit. You can submit to your GitHub repo. And for example, the generated adversary examples and the trained models, we might need this and your code. We need this on a server. So I can run the cross evaluation for you before the task 3 begin. So I will let you know the server after I set up the environment. So for the reports, for task 1 and task 2, you need to introduce the approaches that you are used in the task, and you need to describe the experimental settings. For example, if for AE generation, if you are using FGSM, you need to provide the value of the epsilon you are using, something like that. And if you evaluate the overhead of your approaches, you need to tell us the hardware on which you run the experiment. This slides is available on the GitHub project GitHub. I just uploaded. So you need to cite the previous works. You need to write the report in your own words. Don't just copy paste. And for task 3, because in this task we aim to analyze and investigate the insights of this of your approaches. So basically, you need to involve the methods you used to analyze the data, and any observations. And here, this should be insights, and insights you can draw from your analyzed results and any possible enhancements, future works. So basically, for task 3, these are the discussions, yeah. And you need to provide an architecture of your system, because this is a system class, yeah. And any citations you think is necessary. Yeah. So we will have 3 tasks for each group. You will have around 3 weeks for each task. So here is the schedule for the tasks. And for task 1, it weighs 30% of the project. You will have additional 5% if you generate the AEs using the methods that is not provided in Athena. So if you are using the APIs we provided, that's fine. You can also get the full credit. So for each team, we aim to use 2 to 3 different attack methods. For example, when we mention attack methods, we mean CW or FGSM, something like that. And for each attack, try to generate around 5 variants. For example, if you are using FGSM, so make the epsilons equals to 5 different values. We encourage you to use different configurations we used in Athena. Okay. So after you generate the samples, you evaluate it. Basically, when we evaluate some adversary examples or any adversarial attacks, we evaluate it in terms of success rate of this adversarial example. This is the how successful this attack to fool the model, to fool the target model or any other defenses. So you need to evaluate your adversarial examples on the targeted model. So this is the undefended model. And
so basically, basically aim to generate similar plot, right? But
yes.
more importantly, we expect you to explain what you see in the plot, right? Try to interpret, write your observation in a scientific way, right?
Yes.
What you observe in the data, like briefly, but understandable for anyone. Just do not just plot the result and that's it. You need to also write about it.
Yes. So the undefended model, the vanilla Athena, you can simply evaluate the majority voting and adversarial average probability strategies. So,
but we also encourage you to extend these, as I mentioned, right? Extend these
yes.
Ensemble strategy, come up with some sophisticated ensemble strategy, report the results. These are like whatever you do beyond what we provided here, you will get additional point, and that's what we are looking for, right?
Yes. Yes.
Try to, and these are not really difficult, right? If you are able to do these basic, you should be able to think and come up with some interesting, extensions.
Yes, actually, in this, after I refactor this Athena, I allow different weighted for each weak defenses. So basically, in Athena, we use equal weights for the weak defenses. So in here, it's very easy to extend it to use different weighted for each weak defenses. Yeah, I will also provide this PGD adversarial trained classifier. So you need to evaluate your AEs on this model as well. Okay. So you can plot something like this. And so for the task 2, this is the most important part task in the project. So it weighs 50% with around 10 to 20% bonus. So we have 4 options. You need to claim your task on Piazza before October 15th. I limited the numbers of group as 3, at most 3 for each options. So basically, every option will be selected by at least 1 group. So if you really want to do any task, please claim first. So first come, first served.
Yeah, and to clarify, please follow the same issue that Cody created on GitHub. So put your team there and the task that you selected there in the same issue. So use the same issue as follow-up comments, and we kept track of this over there.
Yeah, I think it's easy. I can show you an example here. Second. So here, I think it's better for you to just, I mean, write down the options you want the most. So in the order you want it most. For example, we are in this Athena team. The team members, Puyang, me, and Jenhai, and we want this task the most. And then this is our second option, and something like this. So if your first priority is full, I will try to check this for you, and so on.
Yeah.
And okay, so the option one for task 2. This task will have you will get
Ying,
10.
do you want, since we are going beyond the class time, do you want to continue on Thursday?
Yeah, I think we can continue on Thursday. This slide has been uploaded to the GitHub, so you can download it from there.
Yeah.
Yeah.
And let's continue on Thursday. Ying will have more information about these tasks and also walk you through some code and discuss some detail. But make sure that you ask all questions because you need to start right away, right?
Yes.
You have almost around 2 months to deliver everything. So
so task one will start next week, October 5th. So next week, now on Thursday, I will go through this with you, and then I will work with you with some tutorial. Show you the codes and show you some tutorial, some samples how to play with Athena. Okay.
Sounds good. Thank you very much.
Thank you.
See you on Thursday. Thanks.
Thanks.